Okay guys, welcome back again. Now, just before we just move on and to define how can we just construct our parameters block, our transformed parameters and also our model, it's essential that we talk a little bit about what is going to be the plan as we just move along. You remember that when we talked in the previous model, we said that if these two coordinates, one of them represents the age, and one of them represents the normalized whole brain volume. We saw that based on the data that we had, we saw that we just have an intercept, although the steepness of the regression line is too steep, but that's simply because of the demonstration. We saw that in our case, if we say that the origin represents 60 years old, and we just go all the way to, for example, 89 years old, you remember that we said that the intercept, which we call that B0, represents the normalized whole brain volume of all the observations that we have at the age of 60. It doesn't make sense because people depending on the different situations that they are. For example, the gender, if they are dementic or not, they have Alzheimer or not, what stages of the Alzheimer's they are in, we expect that the intercept should be different. Then as a result, the thing that we do is that we just move on from this model and we say that, okay, imagine in this scenario, we have a different situation. We say that if still we have the same coordinates, which the x-axis represents the age, and the y-axis represents the normalized whole brain volume, imagine that we have two cases. The first case is going to be the case that the person has Alzheimer or not. Then we say that, okay, we have one intercept, which is going to be for the case that we have non-demented, and we have also one other case if it is with the same slope, it is demented. They have essentially the same slope. In this case, you see that we have defined two different intercepts. We know that we are looking at the ages of 60 all the way until 89 years old. Then we see that we have B0, I call that 1, for the case that the people are non-demented, and also we define B0 2, which means that the case when the people are demented. And also we can find another slope if the case are converted. And now, then we see that then essentially in the model that we are going to explore right now, we have two different intercepts. We expect, or three different intercepts. We expect that people, when they are at the 60 years of age, their normalized whole brain volume is going to be different depending if they are diagnosed with Alzheimer's disease or not. Then if they are recognized with the Alzheimer, we expect that the normalized whole brain volume should be lower than the case that they are non-demented then. And that's essentially what do we mean. Then we just now go back to our R and we define and stand, and when we just want to define our parameters, we look into the fact that now we are in a situation that we talk about the fact that we have changing or varying intercepts, or as they sometimes call that random intercepts. Then we can think of when the case is a random intercept, we can think of it in a case that these randomness, these changes, they can be defined with a distribution. For each, for example, group that they, for example, their intercept changes, we can define them. Let's say, for example, with a distribution that sometimes we can call that a normal distribution with the parameters nu and sigma of, let's say, sigma of the u. And that's the thing that we just want to incorporate that into our model when we go back, I should say, to the R environment. Okay. Now that's the time that we just move on to the R. And now we are just going to define the parameters that we have. Okay. In our previous case, on the model A, we defined our fixed, I should say, effects model. Essentially, the B0 and the B1, which they were fixed intercepts and also fixed slope, they were just defined in the model A. Now, when we just come to the model B, that we are talking about the random or varying or changing intercepts, we do not have those, I should say, those parameters for B0 and B1 because we have them defined on the previous model B1. Then essentially we move on to talk about, I should say, the changing and random parameters in our model. The first thing that we're just going to define, I'm just going to go back to the previous slide. You see that on the previous slide, we said that the whole model is defined in that format. That's our master equation, that the normalized whole brain volume is a normal distribution of a mean and the sigma. Then we define the model based on the nu, either it's going to be linear or non-linear. And the sigma is always there, depending if we have random intercepts or random slope. Then the thing which I'm just going to do, then I'm just going to define this thing. I'm just going to call it the sigma with the, I should say, with the semicolon, and put this one as standard deviation of the model. I know that this one is going to be a real number, which it's going to be the lower, it's going to be 0, because we knew that the measure of the dispersion has always to be positive. If you forget to just put that clause, an argument that this one has to be, I should say, positive by specifying that the lower should be 0, then you get that error when you run your file. Also, the other thing that we just want to define, it's just going to be about, I should say, the model itself. We also call, for example, U. We call that U, which is going to be essentially the distribution of the random or changing intercept. And now, what is the nature of the U? We just call that it's going to be a vector. But when we define a vector, we know that we have to define the length of that vector. We know that the intercepts is going to be different. In the case that we talked about before, if I just want to, let's say, for example, go back to our scenario here, you see that in that case also we can define, for example, another item, which we can call that, for example, B03, for example, somewhere between B01 and B02. Maybe it comes also above B1. We are just going to see that when we just run the model, and we call that, for example, the converted case. Then you see that the length of the vector for all these distributions of the random intercepts, it's going to be 3, which essentially our 3 is going to be defined by the G, which is going to be the number of the levels changing within the group that we have. And also, you remember in the model that we discussed, we defined also a sigma. Let me maximize the window. You remember that we defined a sigma nu. The sigma nu is the measure of the central, measure of the dispersion for the U itself. Then as a result, the sigma, it's going to appear as a different parameter. I'm just going to call it as a sigma U, which is going to be also the standard deviation of the varying intercepts normal distribution. And we know that again it has to be a real number, which it has confined and limited to just be only the positive number. Okay, and now that's that thing. Now at this stage we have been able to define the parameters block for our model, and the thing which is left to do is that we just move on to define our transformed parameters. To define our transformed parameters, which is going to be essential for our model, in order to define the transformed parameters, we essentially giving a kind of a hint of the model that we are just going to define. And what does it mean? It means that we are just going to come here and say that normalized whole brain volume. In this case, instead of calling the replication, I'm just calling it the bar. And I defined it to be as a kind of a vector, which it has a length, which its length has to be, I should say, for the n, the number of the observation. However, I'm just going to define a for loop to capture, I should say, the model, the variations between the random intercepts. I'm just going to call it for I in, let's say, 1. It goes to what? It goes all the way to the number of the n, which is going to be for our model here. I'm just going to put the curly brackets, and I say that the normalized whole brain volume bar, which is going to be for the I, it's going to be essentially equal to a mu, which is going to be the mu that we talked about, that which is going to be the measure for the central tendency of the random intercepts model, plus, and that's what we are just going to do. We are just going to give an index. We said that the u is going to be the distribution of the random intercepts, but we are just going to define it for the group that we are just going to have. And for the group, I'm just going to call that the group is going to be essentially the group I. And when we are done, I have to just make sure that I just put the semicolon there. And when I just put the semicolon there, it means that that's what it's going to be, something that we are going to look into that case at this stage. We see that, okay, for any observation that we have, for which group they are just going to just be defined into. Okay, now we have defined the transform the parameters stage at this model. It's going to be the time, and also there is one parameter which, before I forget and finish this tutorial, you see that we have one parameters here, mu, which we do not have it defined at the parameters block. Because remember, whenever you are defining a parameter, you have to always highlight and specify that in the parameters block. Very simply, I can define it mu as a real number, which defines in the model something like that. And I define the real mu, something as it defines, I should say, the parameters which I have here. By doing this, essentially, we are capturing the information which is coming from the varying and random intercepts in our model for the cases if the observations are demented, non-demented,